Hello and welcome. Today, we're going to demystify a fundamental concept in electrical engineering, the EMF, or electromotive force, in a DC machine. Whether you're a student just starting out or someone curious about how motors and generators work, this video is for you. We'll cover what EMF is, break down its important formula, see how that formula is derived, and look at its real-world applications. Let's get started. So, what exactly is this EMF? First, EMF stands for electromotive force. You can simply think of it as the voltage that is generated inside the rotating part of a DC machine, which is called the armature. This generated voltage appears in two main scenarios. First, in a DC generator. When you rotate the armature's conductors within a magnetic field, a voltage is induced or generated. This is the very purpose of a generator, to create electrical energy from mechanical rotation. This process is governed by Faraday's law of electromagnetic induction. Second, in a DC motor. A motor does the opposite of a generator, it uses electricity to create rotation. But, as the motor's armature spins, its conductors are still moving through a magnetic field. Because of this, a voltage is still generated. This voltage, however, opposes the main voltage that is powering the motor. That's why it's called back EMF. This back EMF is incredibly important because it helps to regulate the motor's speed and the current it draws. Before we jump into the main equation, let's understand the symbols, or variables, that make it up. Knowing what each one represents is key. Here's a quick rundown. E stands for the generated EMF, and it's measured in volts. This is the value we are usually trying to find. P is the number of poles. DC machines use magnets to create a magnetic field, and these magnets have north and south poles. P is the total number of these poles in the machine. Phi represents the flux per pole, measured in a unit called Weber. Flux is a way to measure the strength of the magnetic field. So, this is the amount of magnetic flux coming from a single pole. Z is the total number of armature conductors. The armature is wound with many coils of wire. Z is the total count of the individual wire segments, or conductors, that are actively cutting through the magnetic field. N is the speed of the armature in RPM, which stands for revolutions per minute. It's simply how fast the armature is spinning. And finally, A is the number of parallel paths in the armature. The Z conductors are not just one lone wire. They are interconnected to form several parallel paths. A tells us how many of these paths there are. We'll see why this is important in a moment. Now that we know the players, let's look at the main event, the EMF equation. The generated EMF of a DC machine is given by this formula. E equals P phi Zn / 60A. This powerful formula connects the machine's physical construction, like the number of poles and conductors, and its operating condition, like its speed, to the voltage it generates. But where does this formula come from? Let's derive it step by step. Understanding the derivation makes the formula much more intuitive. Step 1. Flux cut by one conductor per revolution. Imagine a single conductor on the armature. As it makes one complete 360-degree turn, it passes under all the magnetic poles of the machine. If there are P poles and each pole produces a flux of phi, then the total magnetic flux cut by that one conductor in one revolution is simply P times phi. Step 2. Time for one revolution. The speed of the armature, N, is in revolutions per minute. We need the time in seconds. Since there are 60 seconds in a minute, the time taken for N revolutions is 60 seconds. Therefore, the time for just one revolution is 60 divided by N seconds. Step 3. EMF induced in one conductor. According to Faraday's law, the induced EMF is the rate at which flux is cut. In simple terms, EMF equals total flux cut / time taken. Let's plug in the values from our first two steps. The EMF induced in a single conductor, which we can call E, is E equals P phi / 60/N. By rearranging this fraction, we get E equals P phi N / 60 volts. This is the voltage generated in just one conductor. Step 4. total EMF across the armature. Now, we need the total EMF for the whole machine. Remember, we have Z total conductors, and they are arranged into a parallel paths. Think of it like batteries. When you connect batteries in series, their voltages add up. The number of conductors in series in any single path is the total number of conductors, Z, divided by the number of parallel paths, A. So, conductors in series per path equals Z/A. The total EMF of the machine, E, will be the voltage of one path. And the voltage of one path is the EMF of a single conductor, E, multiplied by the number of conductors in series in that path. So, E equals E, Z/A. Now, let's substitute the expression for E that we found in step 3. E equals P∅N/60 Z/A. If we rearrange this to look cleaner, we arrive at our final equation. E equals P∅Zn/60A. And there you have it. That's how the EMF equation is derived. We mentioned the number of parallel paths. Its value depends on how the armature is wound. There are two main types of winding. Lap winding. In a lap wound machine, the number of parallel paths is always equal to the number of poles P. So, A equals P. Lap windings are typically used in machines designed for high current and low voltage. Wave winding. In a wave wound machine, the number of parallel paths is always 2, no matter how many poles the machine has. So, A equals 2. Wave windings are used for high voltage and low current applications. So, how is this equation used in the real world? It's simple. For a DC generator, this equation gives you the actual generated EMF, which is the voltage it supplies to a load. For a DC motor, the equation gives you the back EMF, often written as EB. As we said earlier, this back EMF is crucial because it opposes the supply voltage and is fundamental to how a motor self-regulates its speed and current draw. Let's do a quick recap. We learned that EMF is the voltage generated in a DC machine. We familiarized ourselves with the famous EMF equation, E equals P∅Zn/60A, and we now understand what each symbol means. We walked through its logical derivation and saw how the value of it changes with the winding type. Finally, we saw that this single equation applies to both generators, giving the generated EMF, and motors, giving the back EMF. I hope this detailed breakdown has made the concept of EMF in a DC machine clear and easy to understand. If you found this video helpful, please give it a thumbs up and subscribe for more tutorials. If you have any questions, feel free to leave them in the comments below. Thanks for watching.